So the following section is an introduction to Chapter 8, Solutions and their concentrations. So the first section that you need to look at is Section 8.1, Types of Solutions. And as the instructions say, just read the above pages in the text and complete the following definitions. At the bottom of the page, there are some questions here that you can answer having done some definitions here. But if you get stuck on any of these questions, the information in the next couple of pages might help you to better understand them. The next thing that we're going to look at is the 3 levels of saturation. So we have 3 levels: unsaturated, saturated, and supersaturated. And I often find it best to use the example of a cup of coffee as an example of the 3 levels of saturation. So let's pretend that we have in here a cup of coffee. So here's my coffee right here. Okay, so we'll assume that it's like this. Okay, so in my cup of coffee, I am going to dissolve some sugar cubes. Okay, so I put in 1, 2, or 3 sugar cubes. Okay. Well, what happens? Well, you'll find that the sugar will dissolve in the coffee. Okay. And I mean, a coffee is essentially hot water, right? So sugar is my solute, will dissolve in my solvent. Okay. And what I will end up with, I will still have one phase, right? Because the sugar is dissolved, that creates a solution, right? But this can still dissolve more sugar, or, more generally, can still dissolve more solute. So an unsaturated solution is basically a solution in which you have not reached the maximum capacity of solute. You can still put more sugar into the solution or more solute into the solution and it will still dissolve. And what you'll see here is only one phase. Now, if we kept adding more and more sugar to the cup of coffee, so I added more and more, what's going to happen? Well, if you haven't ever done this, you can try it out. What ends up happening is you get basically a sugar sludge that forms on the bottom of your cup of coffee, right? So the sugar solid rests at the bottom of the cup of coffee because it no longer dissolves. So once you have reached a saturated solution, the sugar, which is your solute, okay, can no longer dissolve into the coffee, which is the solvent in this example. Any added solute will rest at the bottom undissolved. Okay, so basically the sugar is just going to sit at the bottom and it's going to be undissolved there, right? So what we'll have there, if it's sitting at the bottom as a solid, like solid sugar crystal, and we have a solution above it, we have 2 phases. Okay. And essentially, this right here, this solution, there it is now contains the maximum amount of sugar has been dissolved. So that means that this coffee right here cannot possibly get any sweeter. There is a finite point at which it can get its sweetness can be, right? And now if it is as saturated, that coffee cannot hold any more sugar dissolved, right? You add more, it's just going to sit at the bottom. Okay, so we have also the possibility of a supersaturated solution. So a supersaturated solution is a bit different. This is, if we heat up our coffee, what we can do, and then cool it very slowly, what we can do is we can cause the sugar to dissolve into the solution and then remain dissolved. So this ends up being an unstable solution that has a greater amount of solute dissolved than typically permissible at this temperature. So by heating it up, we cause the sugar to dissolve in, and then slowly cooling it, we prevent the sugar from precipitating back out or from crystallizing back out. So this solution is jam-packed full of sugar, okay? And so we should only see one phase if it is supersaturated, right? But because it is so unstable, there's so much sugar that is dissolved in here, a slight disturbance, okay? So a disturbance, which can be in the form of another added crystal, okay, sometimes called a seed crystal, or agitation, causes this solution to go back to being saturated. So all the extra solute that was dissolved in here will come out of solution and form that layer on the bottom, and the solution will go back to being saturated. So it's a very unstable solution. So these are my 3 levels of saturation. Unsaturated, where the solvent has the capacity to dissolve more solute, and increasingly so. Saturated, when the solvent can no longer dissolve any more solute. In this example, like the maximum amount has been reached, and any added solute will just sit at the bottom. And supersaturated is essentially an unstable solution that through manipulation has a greater amount of solute dissolved in that is typically found at that temperature and can be disturbed to go back to saturated through the addition of a seed crystal or through agitation. Now most solutions, as we see here, most solutions are typically solutes dissolved in water. That's generally what we see. Therefore, these solutions would be called aqueous, and for the most part we're going to be dealing with aqueous solutions in this unit. Solute that dissolves in water and conducts electricity are called electrolytes. So anything that dissolves in water and conducts electricity, we give that the name electrolytes. Not every solute that dissolves in water conducts electricity though. There must be, as you recall, how do we know, what is that one requirement for electrical conductivity? Hopefully you'll remember from November because we went over it back then. For something to conduct electricity, you must have mobile or moving charged particles, right? So we'll see in a second why solutes that dissolve in water and conduct electricity have moving charged particles. As we progress through the unit, we'll see why that is, okay? All right, so we're just going to do a short intro into the solubility rule, which is like dissolves like, just a short introduction. Okay. A solute will only dissolve in a solvent if they are similar in terms of their intermolecular bonding. If they are dissimilar, they won't dissolve. Okay. So, for example, sugar, okay, that's a polar molecule, which means that it has delta positive regions and delta negative regions. Now, I know we haven't done this in a while, so it might be helpful to go back and look over your Chapter 3 notes on intermolecular bonding, or just your Chapter 3 notes in general, because they're very much going to play a part in this unit. But let's just try and remember that, a polar region is a region where if it's delta negative, there's electrons pulled in that direction, and if it's delta positive, the electrons have been pulled away from that, okay? Now, sugar does dissolve in water because water itself is polar. Remember, the oxygen in water has electrons pulled to it because it has a higher electronegativity, and the electrons get pulled towards it, so it's delta negative, okay? Now, sodium chloride, remember, is ionic, which means it's made up of positive charges and negative charges. That will also dissolve in water. Because water has positive regions that will attract the negative chlorides and negatives that will attract the positive sodiums. Okay. So this is an example of something that has slightly charged or overall charged being attracted to something that is also slightly charged. Okay, so like dissolves like. Nonpolar solutes will also dissolve in nonpolar solvents. Okay, so a solute will, an example of this is like iodine. Remember that we saw iodine is nonpolar. Okay, we did a lab like this back again in November. Iodine is nonpolar and it will dissolve in something like C6H12, which is cyclohexane. Remember, the CH bond is nonpolar, so generally overall those molecules are nonpolar. Okay. So here's a follow-up question right here. Why does vegetable oil form a layer on top of water instead of dissolving into the water? So for many years you've been probably told, well, vegetable oil has a lower density than water and therefore floats on top of water. But this really has to do with intermolecular bonding. This is not a physics question, but really more so a chemistry question, right? Vegetable oil, okay, is made of non-polar molecules, which don't mix or form solutions with water, which is polar. So the reason why vegetable oil floats on top of water really has to do with the fact that vegetable oil is nonpolar, right? It's a nonpolar solute and water is a polar solvent, so therefore like will not dissolve unlike. Okay? A couple of questions here as well. Some really good thinking questions that will help you sort of make connections. And a supplemental question as well is easy to understand, like dissolves like solubility between polar solvents and polar solutes. Why would ionic solids be included as soluble in polar solvents? And how are they similar to polar solvents? Well, if you go back in the video, we slightly talked about that over here. So maybe rewind about 2 or 3 minutes, and when we talked about this, that helps answer that supplemental question. So moving right along, we're now in section 8.2, factors that affect the rate of dissolving and solubility. So factors that affect how quickly something dissolves. So rate of dissolving is a measure of how quickly a solute will dissolve in a solvent. So I think it's pretty evident if you want something to dissolve faster, you might raise the temperature of the solution, right, or the solvent. And the explanation for that is at higher temperatures, there is more kinetic energy, meaning the solvent particles collide with greater force into the solute particles, breaking them apart more easily. Okay. So for this reason, when we have higher temperatures, dissolving will happen at a faster rate. We can also stir something. So what is it about stirring that allows dissolving to take place at a faster rate? Okay, so when agitated, fresh solvent, and what I mean by fresh solvent, that means solvent that hasn't come into contact with solute yet. Fresh solvent comes into contact with undissolved solute more frequently, causing the solute to dissolve more quickly into the solvent. So just to recap, when we stir solvent that hasn't yet contacted undissolved solute will make contact with that solute, break it apart, and pull the solute into the solution. So stirring is going to speed it up. Okay. And the other thing you might know is that by decreasing the size of the particles will also increase the rate of dissolving. So a very, very fine sugar powder will dissolve much faster than like large sugar cubes or large sugar chunks, right? That should be fairly self-evident, right? So why is that? Well, the surface area of the solute increases as the particle size decreases. So what we mean is, like if we had 1 gram of solute, if that's broken up into tiny, tiny particles, then all those particles have surface area that can come into contact with the solvent, which would cause it to dissolve faster. So therefore, more interaction with solvent, and so it's going to get pulled into solution much more easily. Moving on. So examining how a solution forms between a solute and solvent must be investigated at the molecular level. Solute-solute bonds are the forces that hold the solute together. So like for example, what holds individual sugar molecules together? Well, that would be like the hydrogen bonds or the dipole-dipole bonds between individual sugar molecules, right? And the LD forces. Or for example, what holds table salt together? Well, that would be the ionic bonds, right? Solvent-solvent bonds are also the forces that hold the solvent together. So for example, what holds individual water molecules together in liquid water? Well, that would be the hydrogen bonds. But when a solute dissolves into a solvent, well, the solvent has to break apart to make room to fit the solute in between their particles, and the solute must break apart as well as part of being dissolved. So you end up having these solute-solvent forces are the forces of attraction between the solute particles and the solvent particles. So what determines whether a solution will form? Well, there's two basic cases. So let's just take a look at solute-solute bonds. Okay, so if I have right for here, for example, right, let's say that this right here, this is my solute, okay, and these are my solute bonds. These are strong solute-solute bonds. So what could these be? Well, these could be, dipole-dipole forces. They could be ionic bonds. They could be London dispersion forces or hydrogen bonds. Anyway, these are the things keeping the individual solute molecules bonded together. The solvent, which is generally water, but could be other things as well, I'm going to use that as circles. Okay, and so their molecules are also held together. Okay, they've got forces of attraction between them. Okay. Okay, so these are the solvent bonds. Right, so the solvent then comes into contact with the solute and tries to bond. So this particle tries to bond with this to pull it apart from the other solute particles, right? Well, if these bonds are stronger than the potential attraction between these two substances, so these are, okay, they're just going to try and form that potential attraction. So if this, though, if these bonds are stronger than these bonds right here, well, the solute will stay intact. So the solvent is trying it is attacking the solute, okay, but these are weak solute-solvent bonds. Whereas these are strong solute-solute bonds. Okay. So the conclusion here obviously is that if the solvent cannot pull the solute apart from each other, no solution forms. Okay. No solution, SOL'(N) forms. Now what happens in this example where you have, again, okay, solvent, and then you have solute, but these are comparatively weak solute bonds. Well, once this feels an attraction to the solute, it will likely break it apart. So it will pull the solute apart from the other solute particles. And so what you'll end up happening, or what ends up happening, is the solute particle gets pulled apart and then it gets surrounded by the solvent. Okay, so that is the strong solute-solvent bonds. Okay, and so In this case, because the solute has been pulled apart and has been surrounded by the solvent, we have a solution will form. So there is energy that also is involved in the dissolving process. So when a solution forms, the following must take place, each of which either absorbs energy, so that'd be endothermic, or gives off energy, which would be exothermic. So the solute bonds must be broken so that the solute can disperse throughout the solvent uniformly. So energy is required to break solute bonds, right? Because the solute's attracted to each other, and so energy is required to split the solute apart. Okay, so that right there is an endothermic step, right? It's going to absorb energy. Then the solvent-solvent bonds must be broken to form new bonds with the solute. So energy is required to break solvent bonds. I'll go back to water, right? When water dissolves something, the water liquid has to separate so that the water particles the bonds between them have to separate to make room for the solute particle that will go in between so that they can surround the solute particle. Okay. So then solvent-solute bonds must form so that the solute is held in solution. So when those bonds reform, energy is released when solute-solvent bonds form. Okay, so if something, a dissolution or a dissolving, is exothermic, that means the overall energy from steps 1 and 2, so the energy that is required, is less than step 3. So the dissolving process will release heat and it will feel hot. Okay, so for example, the energy required to break these bonds won't be as big as the energy that is released when the new bonds form. And in endothermic, if the overall energy from steps 1 and 2 is more than step 3, then the dissolving process will absorb heat and it will feel cool. Okay. All right, so that is going to be the end of the first video that deals with the general concepts of solutions and dissolving. So take a look at the homework questions, and thanks for watching.